Hi, we are fourth-year chemical engineering students of the University of Santo Tomas, and we will show you a demonstration of an experiment on Bernoulli's theorem.
Just to give you a brief introduction, in 1738, Daniel Bernoulli stated that with a total mechanical energy comprising the energy associated with fluid pressure, the potential energy due to elevation, and the kinetic energy of fluid motion remains constant.
This theory is supported by the Bernoulli equation. The constant can be evaluated at any point of the stream head. This equation is only valid if the fluid is implicit and incompressible, the flow is at steady state and along the streamline, and lastly, the net frictional forces are negligible.
In the Bernoulli apparatus, which will be used later in this experiment, the fluid flow along the dividing or stagnation streamline slows down and eventually comes to rest at the stagnation point, meaning the velocity at this point is zero.
A common method of expressing pressures is in terms of head of a fluid in units of length. This height or head will exert the same pressure as the pressure it represents.
The objectives of this study are to determine the validity of the Bernoulli theorem on the flow of water by comparing the theoretical total head and the observed total head at a given flow rate, and to determine the range of validity of the Bernoulli's theorem at different types of flow, namely laminar, transitional, and turbulent flow.
In doing this experiment, we will need a Bernoulli apparatus, a digital thermometer, a stopwatch, a 1-liter beaker, and a continuous fluid supply, which is water. These are the parts of a Bernoulli apparatus. So this is the inlet flow. This section is called the test section or the Venturi section. These tubes are called the piezometers, which measures the static head as shown in the column tubes labeled 1 to 6. This tube is called the stagnation tube, which measures the total head. And this part is called the hand pump, which controls or regulates the flow rate of water. And lastly, this is called the outlet flow.
Firstly, determine the diameter for each tapping found at the venture section, and then calculate the cross-sectional areas.
Secondly, allow the water to flow through the apparatus. And then, measure the flow rate by recording the time it takes to fill the 1-liter beaker.
Next, measure the temperature of the H2O. And then do preliminary calculations on the required flow rates that will give laminar, transitional, and turbulent flows for each trial.
Measure the heads of the fluid for each piezometer by aligning the stagnation tube to the desired piezometer. For each reading, always read both the heads measured by the desired piezometer and the stagnation tube. In this case, the stagnation tube is aligned with the first piezometer, so the reading shown by the first tube should be recorded as well as the reading at the 7th tube for the stagnation tube.
Repeat the procedures for measuring the flow rate for the second and third trial with transitional and turbulent flows respectively.
After doing the experiment, turn off the faucet and drain the water from the apparatus.
Finally, clean up the working area.
Now that all the necessary data are obtained, it is important to treat and analyze them to arrive at a conclusion. Our results showed a mean value of 7.58% error between the theoretical and actual total heads for turbulent flow. This implies that for turbulent flow, eddies cause the fluid to move rapidly, thereby violating the assumption of constant density throughout the fluid.
Accordingly, Bernoulli's theorem only applies for laminar and transitional flows having mean values of 0.39% and 0.31% errors from our data respectively. And the relationship between the velocity with the static head and total head as observed is inversely proportional.
We hope you learned a lot from this video. Thank you for watching.
Bye!